Welcome back. Today we will discuss about transformers. We have already learned about transformers in our elementary classes. So from our elementary classes, we know that transformer is a device which converts lower alternating voltage at a higher current into higher alternating voltage at a lower current. So it is a device that converts a lower alternating voltage into a higher alternating voltage. At the same time, the current will be higher when the voltage is lower, right? And when the voltage has been amplified into a higher value, you can see the current is having a lower value. So a lower voltage at higher current, a lower voltage at higher current is amplified into what? A higher voltage at a lower current. That is what is called a transformer. So this kind of relation between voltage and current is to keep the power a constant, because we know power is equal to voltage into current. So a higher voltage at a lower current will be converted to a higher current at a lower voltage will be converted to a higher voltage at a lower current. So that is what is called a transformer. Then what is the principle of this transformer? Transformer is based on the principle of mutual induction. So we have already learned what is induction, what is mutual induction, all those things. So in mutual induction, or a mutual induction is the phenomenon of inducing EMF in the secondary coil due to the change in current in the primary coil, and hence the change in magnetic flux in the secondary coil. So this is the primary section of the transformer. P. S represents secondary section, and this primary is connected to an AC source. This is the symbol of AC source, and secondary is connected to a load. Okay. So it is a phenomenon of inducing EMF in the secondary coil due to change in current in the primary coil, and hence the change in magnetic flux in the secondary coil. So when we pass an alternating current through primary, so this current is coming from a AC source here, there will be a magnetic flux change, right? And that flux will be linked with the secondary. So the change in flux of the primary is linked to the secondary, and that change in flux in the secondary will induce an EMF, right? So an induced EMF will be present in the secondary, and that current will flow through the load. So this is how the transformer is working. Okay. And the EMF induced in the primary will be equal to, say, EP is minus N into d phi by dt, where N is the number of turns of the primary, which is NP. So EP is equal to negative NP d phi by dt. So this EMF is induced due to the alternating current from this source, AC source, and this produces an induced EMF in the secondary. How? Because of the change in the flux in the primary, there is an EMF induced in the secondary, right? So this EMF induced in the secondary, say ES, is equal to minus NS into d phi by dt, where NS is the number of turns of the secondary. Now note that same flux is linked to primary and secondary, right? So our assumption is that same flux is linked to primary and secondary. That is why we are writing d phi by dt. Okay, there is no d phi p or d phi s, because the flux is same, or the same flux is connected to primary and secondary. In other words, d phi is connected to primary and secondary. That is why we are writing d phi by dt. Now ES by EP, we are finding the ratio ES by EP. So ES by EP will be minus NS into d phi by dt divided by minus NP into d phi by dt. Here d phi by dt will be cancelled from both the numerator and denominator, and what is remaining is Ns by Np, and this Ns by Np is called transformer turn ratio. So ES by EP is equal to Ns by Np, and this Ns by Np is called transformer ratio or transformer turn ratio. Now what is efficiency? What is efficiency of a transformer? The efficiency of a transformer is defined as the ratio of output power to input power. So output power divided by input power represent the efficiency of a transformer. Efficiency, the symbol is eta, so this is called eta. Eta is equal to output power divided by input power. That is the efficiency. So what is the physical meaning of efficiency? So you are giving some amount of energy to the transformer, and how much work has been done using that energy. That is the meaning of efficiency. And what is output power? Say P out and divide by P in, and power is equal to what? Voltage into current. So here it is E into I for output. The output part is the secondary part, right? Output part is the secondary part. Therefore P out is equal to ES into IS. That means what? Voltage of secondary into current of secondary, because this is the output part and this is the input part. Okay, secondary represent the output and primary represent the input. Then what is power input? It is again voltage into current. Since input is primary, we can write what? EP into IP. Then for an ideal transformer, efficiency will be 100%. So only for ideal transformer efficiency is 100%. Or this is how we may define an ideal transformer. Okay, an ideal transformer is one for which efficiency is 100%. But practically an efficiency of 100% is not possible. This is because whenever this transformer works, there will be some heat loss, or there will be energy loss in the form of heat, and there can be some other form of transformer loss also. So because of this transformer loss, efficiency will never be 100% practically. Okay, so the transformer efficiency is never 100% because of the transformer loss, and this transformer loss arises especially due to the heat generated during its working. Then which are these transformer losses? Before going to these transformer losses, first we may identify the two types of transformers. One type is step up transformer. So here is the picture of a step up transformer. So step up means the voltage will increase. So from primary to secondary, the voltage will increase, and we may note the number of turns of primary and secondary. For primary, there are only 1, 2, 3 turns, right? There are 3 turns of the conductor. Then for the secondary, we can see 1, 2, 3, 4, 5. There are 5 turns of the conductor. So number of turns of the secondary is more than that of the primary. That is how we may identify a step up transformer. So a step up transformer means it will increase the voltage. So you can see that Ns is greater than Np, therefore Es is greater than Ep, because we have the ratio Es by Ep is equal to Ns by Np. Okay, so if Ns is greater than Np, then Es will be greater than Ep. Then the current is just opposite. If there is more voltage, there will be less current, right? Because this product Es into Is should be a constant. So if Es is more, then Is will be less. So since Es is greater than Ep, we may say Is is less than Ip. That means secondary current will be less than that of the primary current. Then we have the picture of a step down transformer. A step down transformer means what? The voltage of the secondary will be less, or the output voltage will be less. Here again we may notice the number of turns. We can see that the number of turns of the secondary is more than that of the secondary. Here there are 5 turns for the primary, but there are only 3 turns for the secondary. So again Ns by Np is equal to Es by Ep. Since the number of turns of secondary is less, the voltage of secondary is less. Okay, so Ns is less than Np. In other words, Np is greater than Ns. Since Np is greater than Ns, Ep is greater than Es. Again, this product, that is Es into Is, is a constant. Therefore, since Es is less, Is is greater. Or since voltage of secondary is less, current of the secondary is more, or there is a larger current in the secondary than that of the primary. Now, a stepper transformer is one for which the number of turns in the primary is less than that of the secondary. So this is how we are defining a step-up transformer. So a step-up transformer is one for which the number of turns in the primary is less than that of the secondary. Primary number of turns will be less, secondary number of turns will be more. Okay. Then we may define a step-down transformer. A step-down transformer is one for which the number of turns in the primary is greater than that of the secondary, right? So there are more number of turns in the primary than that of secondary in the case of a step-down transformer. Next, we may discuss the different modes of energy losses in a transformer. The first one is copper loss. Heat is produced due to the resistance of the copper windings of primary and secondary coils when the current flow through them. So when current flow through the conductor, this copper conductor in the primary and secondary, this will heat up, right? When current flow through a conductor, that conductor will heat up. And conductor heat up means what? Heat energy is produced. So this heat energy is a wastage of energy. So this is produced due to the heating up of the copper coil. Then second one is flux loss. In actual transformer, coupling between primary and secondary coil is not perfect. So certain amount of magnetic flux is wasted. So we know that in the functioning of this transformer, there is a source of AC for the primary. So because of this alternating current from the source, there will be a magnetic flux produced in the primary, and it is this magnetic flux which is linked to the secondary coil, right? So this changing flux is linked to the secondary coil, and it is this changing flux that produces current in the secondary coil. But the point is, there will be some flux in the backward direction also, right? There will be flux produced in the backward direction, and also there will be flux produced in to the two sides of the transformer also. So these flux will not be linked with the secondary. Only the flux which are moving in the forward direction will be linked to secondary, and all other flux will be a mere wastage because this will not be connected to the secondary. So this flux loss is another source of energy loss. So this is how the flux will be produced. So this flux which are moving in the backward direction will not be connected to secondary. So this flux is a loss for the functioning of the transformer. The next one is eddy current loss. When a changing magnetic flux is linked with the iron core, eddy currents are set up, which in turn produce heat and energy is wasted. So we have already learned that eddy current is produced in a block of metal, right? So when this block of metal or this metal core is in the magnetic field, there will be a current produced in this core of the transformer, and this eddy current is a mere wastage of energy. Why? because this eddy current cannot be taken out. So the energy which is used for the production of this eddy current is a wastage of energy as far as a transformer is concerned. So this is the eddy current laws. Next, hysteresis laws. When alternating current is passed, the iron core is magnetized and demagnetized repeatedly over the cycles, and some energy is being lost in the process. So this iron core of the transformer is in a magnetic field, and this changing magnetic flux will repeatedly magnetize and demagnetize this iron core, and this continuous magnetization and demagnetization will lead to an energy loss which is called hysteresis loss. In the previous class we have already learned about the magnetic hysteresis loss. So these are the different modes of energy loss in the case of a transformer. So that's all for today. Thank you for watching.